Welcome everyone to the third mini course of our workshop at the Lawrence Center. My name is Max Lein and I would like to give you a brief introduction to some of the semi-classical methods that are applied to condensed matter systems. This is an online-only conference, and this is in fact my first time doing a mini course in this setting. So I've decided to stray a little bit from the usual way to do things, and instead of uploading one or two very long videos, I've decided to break it into smaller videos, about 25 to 30 minutes a piece. At least that's the plan. And furthermore, I have uploaded all of the references that I'm going to mention to the Microsoft Teams platform provided by the Lawrence Center. In case you're watching this after the fact or you don't have access to the Microsoft Teams platform, then I just suggest to you that you send me an email, and I will be very happy to provide you with all of the references that you're interested in. So let's get started. So this here is a sketch of the situation that we would like to describe using effective semi-classical approximations. So this black slab is our sample. Of course, because I'm limited by my drawing abilities, this is either a 3 or a quasi two-dimensional sample. So you can see this direction is very thin, but mathematically speaking, the formalism works in any dimension. So in experiments where you want to decide whether a material is a conductor or an insulator, what you do is you apply a voltage. This voltage, in fact, you apply voltage difference. This voltage difference gives rise to an electric field. So this is the gradient of the voltage difference in a sense. So that gives you the electric field. And then you measure a current that is not necessarily parallel to the electric field. So here, just for pedagogical purposes, I've just drawn a situation where the two are almost orthogonal to one another. But this is just a little bit of an exaggeration to make it a little bit easier to see that the applied electric field and the measured current need not be parallel to one another. So these are really vectorial quantities as indicated by the little arrows on top. And then in addition, you can have other external parameters like the temperature or a strain or a stress, but also commonly a magnetic field that changes some of the properties, some of the conduction properties of the sample. So what we would like to know now is, starting from a microscopic model, can we infer or predict the conductivity properties of a material? So first of all, the electric current itself is not a very good quantity to study, and the reason is relatively benign and simple. The electric current scales with the volume, and if we idealize the situation by looking at an infinite crystal, for example, a sample of infinite size, then the current would either be infinite or zero. So that's not very interesting. So instead of using the current, we study the current density. And the current density, let me write this as J of t. This is the expectation value of the current observable with respect to the time-evolved state rho of t. So this calligraphic J is the expected current, or rather expected current density, E is the expectation value, rho of t is the time-evolved state, and J is the current observable. I'm being intentionally vague here. So the expectation value could be a classical expectation value, or it could be a quantum expectation value. So for example, if we were to use a quantum mechanical description, the appropriate expectation value here would be the so-called trace per unit volume. And in a classical description, the current observable would be the elementary charge, E, times the velocity. Of course, you can also look at it in a quantum picture. Then this would be I times the commutator of the position operator with the Hamiltonian, up to a proportionality factor, of course. And it is this quantity that you can measure in experiment. Of course, you will measure the total current, but then you can also compute the current density. One of the early successes of quantum mechanics was to give a microscopic model that allows us to predict or explain why some materials are conductors or metals. So I'm calling a material a conductor or metal if the current density is appreciably different from 0. And materials that do not conduct electricity very well are insulators. So here J is very, very small, mathematically speaking. It is 0. So now, what is the purpose of this lecture? Well, what we would like to do is we would like to start with the quantum equations. So this is the main goal. We would like to start with the quantum equations. So here the dynamics is governed by the Schrödinger equation, of course. So it's I epsilon, the time derivative of the wave function. So epsilon is the semiclassical parameter. I will explain everything in more detail in due course. And the dynamics is governed by the Schrödinger operator that I will give below. Importantly, the initial state, so for simplicity, I'm taking the initial time to be 0. This comes from a relevant subspace. Which is a subset of L2 to the RD. So, of course, you can think of situations where you include spin and the like, and then, the Hilbert space will be slightly different, but that is not an important point here. And the Schrödinger operator that we're looking at is that of a non-relativistic particle in RD. As the picture suggests, we're applying an external magnetic field. So I have to add the magnetic vector potential. So this is the kinetic energy in the presence of a magnetic field. Then I have a periodic potential that is due to the atomic nuclei and all other electrons. So this is in the single electron approximation. I'm neglecting electron-electron interactions. And lastly, I have to add an external, meaning slowly varying electrostatic potential that generates the electric field E here. So the A generates the magnetic field, the E is the potential, the phi is the potential for the electric field. And then under very mild conditions on the potentials, you can show that this is indeed a self-adjoint operator on, for example, typically the second magnetic Sobolev space. And okay, at least formally speaking, once we've ensured self-adjointness, we can solve this Schrödinger equation in closed form. And the dynamics is given by the unitary evolution group. So it's e to the minus it divided by epsilon h a epsilon applied to the initial vector psi naught. And importantly, so this is something that needs to come out of the analysis. And let me add quotation marks here, because this need not be true exactly. This can be true just approximately. But the time-evolved state should stay in this relevant subset, or in this relevant subspace, rather. So just to write down the connection between the fields and the potentials. So the electric field E is minus the gradient of phi, and B is if you interpret the magnetic field as a 2 form and the vector potential A as a 1 form, this is just the exterior derivative of A. But of course, what you can also do is you can identify this in a canonical fashion once you choose a basis with a matrix of components. And this will be useful to write down the right-hand side, the semi-classical equations, in a more compact way. So these are the quantum equations, and the claim is that these can be approximated by semi-classical equations. So in the simplest case, to leading order, you would get an equation for the velocity, r dot, which is just plus the k gradient of a so-called energy band function En, plus higher order corrections in the semi-classical parameter, perhaps. And then you have an equation for k dot, which is crystal momentum, which is just minus gradient phi, so that's the electric field, plus b r dot plus order epsilon. So this here, physicists would just call this here the Lorentz force. So just a small explainer here. So here I've used the identification between the 2 form and the matrix of its components. So this would then be a d by d matrix multiplied with the d vector, which gives a d vector which is exactly right, dimensionally speaking. And because these are Hamiltonian equations of motion, this is an ODE, what we have here is a solution. So the dynamics are given by the semi-classical flow. And it is not at all clear how to actually do this, right? So let's just try and parse this a little bit further. So on the quantum side, the dynamics are given by the unitary evolution group. So let's color this in green. And the semi-classical analog is the flow. So the flow acts on, in this case, on a cotangent bundle on a symplectic space, whereas the unitary evolution group acts on a Hilbert space. So how do you compare them? How can you say that one is similar to the other? It's not at all clear. So in fact, this is goal 1. So we have to explain how to compare the 2 evolutions. And there are some important details that you might have missed at first reading. And one of them is that this semi-classical limit, the way it's written down here, is only valid for certain states. So here we have a correspondence between this relevant subspace and the so-called energy band function. So if you choose a different relevant subspace, either it's not going to be possible to do a semi-classical approximation, or if it is, you would have to potentially use a different energy band function. And like I said before, on the semi-classical side, so that's also why these are not classical but semi-classical equations of motion. Quantum mechanics still enters through the energy band function, and this is not obvious because I've not made them explicit, also the higher order corrections. So these will depend on quantum mechanical quantities in an explicit fashion. So the conceptually what we're doing here, and this belongs to point 1, we're doing a trade, right? And like so many things in life, we have to give up something to get something. So on the left-hand side, we have a linear PDE. So it's a partial differential equation, and it is linear. And we would like to approximate it by a nonlinear ODE. So this is the trade that we would like to make. The second point is that we would like to be able to compute also higher order corrections. This is because very often interesting physics is contained in the sub-leading terms. So the leading terms have quote-unquote trivial dynamics. Trivial in this case just means well understood, or in some cases, so if this were an insulator, could lead to zero conductivity, but the sub-leading terms can still give you a non-zero contribution to the conductivity. So it is really these terms that you would like to obtain and compute. Connected to that, of course, is that we would, since this is supposed to be at the intersection of math and physics, we would like rigorous control of the remainder, or of the error if you want. And lastly, we also have to worry about the time scale of validity. Why is that? Well, just go back here. On the left-hand side, we have a linear PDE, and if we approximated a linear PDE by another linear PDE, then we know that the error can at most grow linearly in time. So this is relatively simple. But if you are approximating a linear equation by a nonlinear equation, you usually have to involve the Grönwall lemma. And this gives you a limit on the time scale of validity, because even if you just compare two nonlinear ODEs that are where the vector fields are close, if you wait long enough, then the trajectories typically will diverge exponentially. So this gives rise to chaos. And the same can be true here, right? So this is, of course, tightly connected to rigorous control of the error. So the error can only remain small on a certain time scale. So the best that you can do is a so-called Ehrenfest time, but typically in semi-classical approximations, we work with bounded times. So times that do not scale with a semi-classical parameter epsilon. All right, so before I go to the meat of the issue, let me just finish by asking the question why we should do this in the first place. So I came up with three distinct reasons. Of course, this is a little bit my personal taste, and perhaps at least one of them might be a little bit out of date. But still, I think this is worthwhile to at least attempt to answer before we proceed. So the first thing is, and this is especially true in the beginning, is ease of computation. In the early times of quantum mechanics, people simply did not have any access to computers, certainly not the types of computers that we even carry in our pocket these days. So it was either not possible or at least not practical to simulate systems like this in condensed matter using the quantum mechanical equations. So what people did was they tried to work with simpler systems that can be simulated more easily, and this is a semi-classical model. So this is what Lifshitz did with his co-workers in the late 1950s. So Lifshitz, Karganov, and Abel in 1957, Lifshitz and Peshansky in 1959. So the late 1950s, they came up with using semi-classical equations of motion to study condensed matter systems. And then later on in the Western Hemisphere, there was an important work by Zak in 1968 that also kicked off this type of study in the West. So this is perhaps a reason that, okay, you could claim is perhaps a little bit outdated. But I think it might still be better to work with semi-classical equations if you can, because one thing that I always tell myself and my students is that you should work smart and not hard. So even with computers, simulating a quantum system is much more involved in terms of CPU time, in terms of the methods that you need to use, compared with a simple Hamiltonian ODE. So this can be simulated much more efficiently. So for each, let's say, minute of computing time, you can do much more with a semi-classical description than with a quantum description. And this, you could say, well, if you know from good theoretical arguments or even mathematical proofs, which are better, that the semi-classical approximation is accurate enough for your intents and purposes, then it might just be better to use the semi-classical approach. But lastly, there's also one more aspect that I think is quite important. And that is, if you think of thermodynamics, I can simulate a gas using, say, Newton's equations of motion. So I put 10 to the 3 atoms inside of a fixed volume. And then I can solve, at least theoretically speaking, I can solve Newton's equations. But what you get out is not necessarily useful, right? If the system is in thermodynamic equilibrium, it's much more efficient to instead specify the state of the system using pressure, temperature, volume, and depending on if you, for example, allow the exchange of particles, you could also have other thermodynamic quantities. But the point is, rather than having 10 to the 23 positions and momenta, you have, let's say, 3, 4, 5 thermodynamic variables that give you a much more efficient description than a microscopic simulation. And also more insightful, right? So this is, let's say, the just the introduction. I will catch up with you when we start to talk about the background.